everyone, welcome to the course on medical biomaterials. We will continue on the topic of polymer blends, composites. We have been discussing about these blends and composites, and we will spend some more time on that. So, let us look at a problem. Calculate the density of mineral phase of dried cow femur. Density is 2.06. This is a dried femur. Okay. For example, if you take this cow femur, it will contain a mineral phase just like hydroxyapatite, and then there will be an organic phase, okay, like collagen, and then there will be water. Okay. So, the density is 2.06. This femur contains organic, mineral and water. Because it is dried, there is no water. The density of organic is 1. So, organic to mineral is 1:1. So, we can use the mixture rules. It is quite simple. Okay. So, density of the femur is 2.06. Okay. Then we have density of organic is 1 into 0.5, density of mineral phase, that is what we have to calculate, into 0.5. So, this is equal to 2.6. This is the density of the femur. So, we can calculate this from this. Okay. So, the density of the femur is equal to volume fraction of the organic into density of organic plus volume fraction of the mineral into density of mineral. Water we have ignored because it is dried. So, the density of mineral is given as 1.12 gram per cc. This problem was taken from this reference. Let us look at another problem. Calculate the percentage load borne by the mineral phase of a cow femur subjected to 400 Newton. Okay. So, as you know, it has got mineral, it has got organic and then water. So, mineral is about 44%, organic is 40%, and there is water. So, water will not take any load. So, mineral and organic. Okay. Young's modulus of mineral phase is 17 gigapascal. Young's modulus of organic, which is collagen, it is 0.1 gigapascal. So, the load borne will be proportional to the ratio of the composition. That is simple actually. Okay. That will be the ratio of the composition, because we will take only the mineral and organic here, we will ignore the water part of it. Okay. So, load of the mineral phase, load borne by the mineral phase divided by load total, that will be Young's modulus of mineral is 17 gigapascal, and it is 44%. So, 0.44 into 17 divided by the total 0.44 into 17 plus 0.4 into 0.1. You understand, this is the total, that is 0.4 into 17 plus 0.4 into 1, and then the mineral part is 0.44 into 17. So, that gives you 0.9947, that is 99% of the load will be borne by the mineral phase. Okay. Because the Young's modulus of the mineral phase is so much, Young's modulus of the organic phase is very little. So, it is assumed that it will be in the same ratio as the Young's modulus and the volume fraction. Understand? So, it is quite a simple problem. So, when we have multiple materials, especially say in composites, then the load borne by each of the item will be based on their Young's modulus, respective Young's modulus, and their respective volume fraction. So, you need to remember that. Okay. So, composites, as you know, combination on a macroscopic level, two or more materials different in morphology and physical properties, like we are putting say silicate and a polymer, or carbon fibers and a polymer, okay, or some alumina and some other polymer, like that, you know, two different materials of two different morphologies as well as physical properties. For example, like I showed you the composite material, the inorganic may have a very high Young's modulus, the polymer may have a very low Young's modulus. Okay. That is the physical property change. They exhibit properties that the single constants do not have. So, obviously, it will not be based on the single component, but it will be based on their individual pure values and the ratios. It is tailorable to specific application. So, we can have different compositions of the organic and the inorganic material. Okay. If I am having carbon nanofiber, I can change the composition of the fiber. If I am a glass beads in a polymer, I can change the composition of the glass beads. Okay. So, reinforcement it provides the mechanical strength. Matrix, that is the polymer, binds the reinforcements and distributes the load. So, suppose I have 1% fiber and I have say 99% PMMA, then that matrix distributes the load. Okay. Sometimes we need to add additives, fillers to provide special attributes. That means if for mixing say the inorganic with the polymer, we may have to add some surfactants, surface active agents or some other hydrophilic polymers and so on, actually that is called additives and fillers. That is how a composite is made up of. Applications: catheters, they are used silicon rubber reinforced with silica particles. Okay. It provides, the silica particles provides, improves tear strength and reduce wettability. Polymers like PU, LDPE, PVC reinforced with nitinol. Nitinol is a nickel titanium alloy. So, with this we can achieve very thin walls, we can have controlled stiffness, high resistance to kinking. Otherwise, if you have just these polymers, the tubing may get kinked. So, we add this alloy. Cartilage replacement, we can have poly PVA or hydroxy, propyl, methyl, cellulose with silica. This gives you, the silica gives very good mechanical properties to the cartilage. Carbon, glass or aramide fibers in thermosetting polymers. Okay. So, a lot of these are added to give strength, to give toughness, it enhances strength, it enhances modulus. Carbon fiber, high stiffness, okay, high tensile strength, low weight, high chemical resistance, high temperature tolerance. So, that is why carbon is used quite a lot. Carbon reinforced polyether ketone, okay, for bone plate screws. Flexural and fatigue properties comparable to that of stainless steel, spine plates and screws. Okay. Whereas this polymer may be very light. So, by adding this carbon we are getting very good flexural fatigue and flexural properties equivalent to stainless steel. Silica glass fiber reinforced PMMA used in dental fillings. Okay. The fiber gives the toughness. Carbon reinforced polyethylene used in knee prosthesis. Okay. There is a lot of attrition, there is a lot of bending, flexural, the carbon fiber gives. It gives improved compressive, tensile, elastic modulus, fatigue strength, undergoes less wear, undergoes less percentage deformation even under high stress, whereas polyethylene may have higher wear, may have more deformation. Carbon fiber reinforced polysulfone, plates, screws, spinal segmental replacement implants. It is quite semi rigid actually, it is not fully rigid, but it is not soft like this polymer. It could replace metal alloys in orthopedic. The advantage is it could replace and they are quite lightweight also. Carbon fiber reinforced bone cement, improved fatigue strength because of the carbon fiber. It reduces the incidence of cement fracture and loosening of the prosthesis. Glass fiber reinforced acrylate, again it is very good for dental composites, bone cements. It gives, strengthens the fixed partial dentures. Thermoset polymers, composites reinforced with glass, carbon, Kevlar, prosthetic limbs. So, you see these carbon fibers, glass fibers, they give strength, flexural strength, yield strength, improvement in modulus, improvement in wear when you compare polyethylene or PMMA type of polymers. Also they are used quite a lot in medical instrumentation. Carbon fiber reinforced polymer used in tables of MRI, CT scanners, that gives you strength, that gives you stiffness, and of course they are lightweight. If I am going to use a complete metal, it is going to be very heavy. So, a polymer will be very lightweight, we can strengthen it with carbon fiber. Radiolucent, okay, so it will prevent penetration of light wave, radio waves. Non-magnetic to obtain clear sliced images of, whereas if I have some metal, they could start interfering because of their own inherent magnetism. Surgical clamps, headrest frames, X-ray film cassettes, CT scan couches. So, a lot of medical instruments are nowadays being area where metals are getting replaced with polymer reinforced carbon fibers or glass fibers and so on actually because of the lightweight. Okay, now we can also achieve good tailored properties by blending polymers, two polymers blended together, okay, So we get properties which are not found in individual polymer. One method is, there are many methods of these blending. One is called the solution casting. It's a mechanical mixing of polymers in solvents and casting. Melt mixing, that means you melt the polymer. Here we are not using any solvent, but we are melting the polymer at its processing temperature, okay, and then mix them. So the blend morphology depends on the mixing temperature and time here, whereas in the previous case you are dissolving the polymer and casting. Co-precipitation, polymers in the blend precipitated simultaneously or spray dried, okay, or solid polymer blend. So you blend them together as a co-precipitate. Electrospinning of mixture of polymers, that means we take two polymers in the solution, okay, and then electrospin it. So you get loosely connected 3D porous mats with high porosity, high surface area, which can mimic extracellular matrix. So what is this electrospinning? Let us look at the electrospinning process. It is a combination of electrical field and spinning. So you can spin the polymer blend like ions. So we can get a mat of ions. So what do? You take the solution, the mixture of polymers, and then you force it through the nozzle, and then you apply a high electric field here. So you may have a melt or a solution coming out of the tip of the die, and it has charge. Then you apply another charge on the collector plate, okay, that leads to the droplet deformation and ejection of charged jet from the tip of the cone. So it gets accelerated towards the collector electrode, leading to the formation of continuous fiber. So you force this melt polymer solution or the polymer in solvent, mixture of polymers in solvent, you apply a high voltage. So the droplets which come out are charged, then you connect the other okay, side of the voltage. So they go and get deposited and collected, okay. So that is the advantage of this. This is called electrospinning, and this is called electrospinning. So we can get a very nano sized fiber diameter, we can get ions of them, and it is quite used in wound dressing applications. It is also used when you are trying to make scaffolds, because the ions are very small in diameter and they are very porous, okay, many gaps. So cell growth is very facilitated, that is called electrospinning. So these are different ways by which we can mix polymer and prepare polymer blends. Sometimes we need to add some additives, they are called compatibilizers, to improve the compatibility of immiscible polymers. You may have a hydrophobic polymer, you may have a hydrophilic polymer. So we may have to add something, sometimes we add PVA, which is very hydrophilic. So these are called compatibilizer. They improve the interfacial attraction between these two polymers, and thus the morphology and the resulting property. So many times you will see PVA is widely used. So addition of AB block copolymer for blends of A and B. Addition of linear random copolymer. Random copolymer will be amorphous, it will not be crystalline, so it may blend better with two immiscible polymer. Interpenetrating polymer, blend in network form, one polymer synthesized in the presence of the other. Crow reaction in the blend, like you can do transesterification, okay, in the presence of another polymer. So this can lead to different copolymers. Or we can do cross linking, we have two polymers, then I say I use glutaraldehyde or I use some other cross linking agent, so that there is a fixed covalent bond formed between the polymer. Addition of co-solvent. So what you do is immiscible polymers dissolved in a common solvent, after evaporation large interfacial area stabilizes this polymer interaction, that is called the addition of co-solvent. So many methods are there, they are all called compatibilizers to improve the mixing or blending of two polymers. If the blending is not good, you may end up having a heterogeneous mixture of polymer A and polymer B, regions where you may have more of A and less of B, and regions where we will have more of B and less of A, which is not desirable. We want a very uniform okay, macroscopic mixing of these two polymers. For example, if you look at PVC blends, PVC is widely used, PVC is quite inert, PVC nitrile rubber gives the very good flexural property. Permanent plasticization, excellent flow, physical properties, long term stability, resistance to chemical and oil, good electrical property. This is used oxygen mask, IV tubes, regulator, gloves. So, we need good flexibility because PVC is not so flexible. By adding this nitrile rubber you are improving that. PVC with PMMA gives you toughness, impact resistance, durability, processability. So, they are used in medical equipment, housing, MRI fixtures. PMMA has good toughness, PMMA is very transparent, it is widely used in dental application. PVC is very inert, okay, good lubricity. So, mixing them they are used in medical equipment. PVC with ABS, okay, high heat resistance, good weatherability, good processability, again in medical instrument. PVC with PCL, clarity, flexibility, toughness, used in bags, pouches, tubing, drug delivery. PVA, ethylene vinylene acetate, clarity, flexibility, bags, pouches, tubing. So, you see even PVC, although it is used quite a lot in medical application, especially in drain tubes, catheters for short duration, some of its disadvantages are overcome by adding another polymer to improve those properties, okay. Especially as you can see, lot of bags, pouches, medical instrument parts, housing, gloves, external, lot of external biomaterials are prepared using this. Other example of blends, polydioxane elastin blend, vascular graft, polydioxane gives strength, elastin gives flexibility and bioactivity, so which can be recognized by cells, okay. So, this polymer gives the strength, this gives you the bioactivity and recognition. So, they are used in vascular grafts. Polyethylene polyurethane blend, tympanic membrane replacement, transparent and flexible, the flexibility comes from polyurethane, okay. It has got a higher modulus than polyurethane. Silicone PHEMA, okay, lens material, because this is anyway used hydroxy ethyl methyl okay, acrylate is used in soft contact lenses. Silicone, we are improving the oxygen transmittability as well as it gives you stability as well. Polycarbonate polyester, okay, polycarbonate is very strong, rigid, tough. So, these blends are used diagnostic equipment, respiratory therapy devices, they are also chemically resistant because polycarbonate is also chemically resistant. So, it becomes very tough polymer. Carboxymethyl cellulose, PVP, polyvinyl pyridinone, and this is a natural polymer used in wound dressing, okay. CMC does not have any strength, so PVP gives the strength, okay. So, together they have very good strength as well as flexibility, they have good water uptake, enhanced biodegradability. So, you can see PVP carboxymethyl is very useful for wound dressing application. So, lot of examples of blends being used, mixing two polymers together, so we can achieve properties which is not available with one single polymer, and sometimes we may have to add compatibilizers, that means a third polymer which improves their mixing, or we can do a cross linking and so on actually. Then we also looked at composites where we are adding an inorganic material, okay, like your glass or carbon fiber or particles into a polymer. So, it gives a lot of strength and better elastic modulus, okay. So, let us look at one or two problems, okay, on this topic. A biodegradable polymer when implanted in a rat loses 40% of its tensile strength in 10 days and 50% of its tensile strength in 20 days. So, how many days it will take to lose 60% of its strength, okay. That is quite simple. So, we can assume exponential decay in the biodegradability. So, we can say strength is equal to original strength exponent minus kT, k is a constant, sigma 0 is the strength at time 0. Okay. So, in 10 days it loses 40%, so there will be 60 left behind. In 20 days it loses 50% or 50% strength left behind. We can calculate sigma 0 and k, and then for the next part of the problem, for a 60% loss of strength, what is the time? That is what you have to do. Okay. So, you understood the problem. So, first part 40% it lost in 10 days, so remaining is 6. 0.6 is equal to sigma 0 exponent minus 10 k, 10 is your days, 50% lost in 20 days. So, 0.5 sigma 0 exponent minus 20 k. So, k is not known, sigma 0 is not known, 2 unknowns, 2 equations, sigma 0 is 0.72, k is equal to 0.018. Units of k is okay, day inverse, because t is day. Now, how many days will it take to lose 60% of its strength? That means 40% is left behind, 0.4, 0.72, 0.018 t. So, we need to calculate t, that is 33 days. It is quite a simple problem, but it is a very interesting problem to work at. It gives you a nice idea about the main point here is we assume the biodegradability leading to loss in strength follows a exponential type of decay. Okay. That means it is like a first order loss, sigma is equal to sigma 0 exponent minus kT. It might not be true, but it is good enough for us to assume, so that we can use this equation and the whole data to calculate for the new unknown. Okay. That is the advantage. So, this example was taken from this particular reference, so I thank them. Let us look at another problem, and this is related to a composite problem. So, look at this carbon reinforced okay, PMMA, carbon reinforced PMMA is prepared for bone fracture application, fracture plate. Okay. So, as you know, carbon fiber has very high modulus 250 gigapascal, PMMA has very low 3 gigapascal. Look at the density is 1.95, 1.2. Strength of carbon fiber 5000 megapascal, strength of PMMA is 70. Calculate the amount of fiber required to achieve a modulus of 100 gigapascal. So, we have two materials mixed together for a composite, we want to achieve 100 gigapascal. So, we can follow the mixture rules, volume fraction of carbon multiplied by 5000 plus volume fraction of PMMA multiplied by 70 will give you 100, and of course, volume fraction of this plus that should be equal to 1. So, we can calculate what should be the amount of fiber to be added, quite simple. Look at this 100 volume fraction of carbon fiber okay, into 250 okay, volume fraction of PMMA 1 minus volume fraction of carbon okay, into 3 . So, we can get from volume fraction for carbon fiber is equal to 0.39. So, I need to add 0.39 or 39% carbon fiber and remaining 61% PMMA to achieve a modulus of 100 gigapascal. Okay. Or same thing we can do if you want to look at the strength, the same. So, the same volume fraction ratio is what it follows, and that is called the mixture rules. Understand? Okay. So, we can multiply by the corresponding volume fractions okay, to get the overall modulus, or if you want to calculate the maximum strength it can take, we can multiply their volume fraction to these strength and then add them up. The second part of the problem, cross sectional area of the bone plate is 1 centimeter square and the fiber diameter is 10 micron. Okay. How many fibers are required? Assume they are aligned in the same direction of the force. So, volume fraction of the fiber is 0.39, okay. Cross sectional area of bone plate is 1 centimeter square. So, if I assume L as the length of the bone plate, volume of the bone plate will be 1 into L, okay. I am having a 10 micron diameter. So, if I take it as a circular, pi d square by 4 it will come, okay, multiplied by n, okay, that will be the volume fraction for the fiber, total fiber occupied, that will come from here 0.39, okay. So, from there we can calculate number of fibers. So, volume of the bone plate 1 into L, L is the length of the bone plate, volume of the fiber pi 3.141 multiplied by radius is phi r square, phi square. This is for converting micron to centimeter. Length is the length of the fiber because the fiber is along the bone plate, n is the number of fibers we take. So, this will be equal to volume of one fiber area into length multiplied by n fibers, okay. So, this divided by this should be equal to 0.39 because that will be the total volume fraction of the fibers. Do you understand this problem? So, 3.141 multiplied by phi square multiplied by 10 minus 8 L n divided by 1 L, that will be the volume fraction of the fibers, which we have calculated in the previous is 0.39. So, n is equal to 5 into 10 power 5, okay. So, 5 lakh fibers are needed of 10 micron diameter, okay, for this bone plate of 1 centimeter square area to achieve a volume fraction of 0.39. You understand? So, cross section of a bone plate is 1 centimeter square. If I take length of the bone plate is L, 1 into L will be the volume. Take one fiber, pi r square L, r is 5 microns. So, pi into r square phi square, this is converting the micron into centimeters, okay. As you know 10 power 4 micron is 1 centimeter, okay, that is why you got 10 power minus 8 L. There are n fibers, so we have put n here. Now, this term divided by this term should give you 0.39. So, from there we can calculate n. So, I need 5 lakh fibers to achieve a volume fraction of 0.39, okay, if the cross sectional area of the bone plate is 1 centimeter square, okay. Third part, how much stress in the fiber direction can the bone plate take, okay, stress, same thing like I said before, 0.39 is the volume fraction of your fibers. So, 0.61 will be the volume of PMMA, 5000 is the strength of the carbon fiber, that is stress, 70 megapascal is that of PMMA. So, we use the same mixture rules. So, 5000 into 0.39 plus 70 into 0.61, that will give you 1992, okay, megapascal, okay. That will be the stress this whole bone plate will take. But of course, you need to assume, you need to consider that the fibers are all aligned in the same direction as your bone plate, but in reality some of the fibers may not be aligned. So, they will not be able to take in the same force, only the fraction that is aligned will take in the force, whereas those that are not aligned will take in much lesser force, okay. So, in reality the stress the composite may take in may be much lesser than this could be the best case scenario, okay. So, with that we conclude on the topic of composites and blends, polymer based blends as well as polymer and inorganic material based composites. Thank you very much for your time.